So hello everyone, I'm Gitanjali Jaina. So I'm a PMRF scholar from IIT Delhi and the TA for this course, which is Physics of Linear and Nonlinear Optical Waveguide. So, so let me connect my tab first, then we'll start our session. Okay, so I think my screen is visible now. So let me start from the first question. Okay. So we basically will see step index optical fiber. So in the previous live section, we mostly gone. Okay, it's visible now. Okay, so we'll start from the first question. So towards the end of this live section, I will give a hint about how to. So I saw a few questions about using MATLAB or any software to solve the transcendental equation to find out what are the LP total number of LPLM modes, what are the propagation constant of LP02 modes. So I will give a hint about how you can solve it using MATLAB. So just use the hint to solve the problems related to the assignment. Okay, so let me start. So the first question, it says tape index fiber with refractive index N1 is 1.5, N2 is 1.49. And it is also given what is the core radius, which is 3 micrometer. Then it was asking what is the calculate the range of lambda 0 for which LP01, LP11, LP21 and LP02 mode exit. So, if you recall, we have for a optical fiber, we have linearly polarized modes, which are indexed as LP, LM modes. Okay, so let me draw the BV curve. So we have a curve like this. So this curve tells us about what are the allowed condition, what are the cutoff condition. So all the information you can get it from the plot between B and V curve. So the maximum value of B is it is 1, and the mode that is always guided inside the fiber, it is LP 01 mode. So it is no cutoff. Really, it is always guided, which is LP01 mode. And the second mode, which is LP11 mode, it is a cutoff around 2.4048. So second mode, it is LP11 mode. It is a cutoff around 2.4048. And the third and fourth guided mode is LP21 and LP02. So these two modes have same cutoff. So LP02, one is LP02 and one is LP21. So these two modes, they have the same cutoff, which is around 3.8317. And the question it is asking about the value of lambda 0 for which these modes exist, right? So how did you get the cutoff condition? If you recall, we have transcendental equation, which is v root over of 1 minus b, j1 v root over of 1 minus v whole divided by j0 v root over of 1 minus b, which is equal to v root over of b k1 v root over of v whole divided by k0 v root over of b. So this is for only for the case when we have L equal to 0. So when L equal to 0, you can use this transcendental equation, which is let us LP01, LP02, and like this. For the case where we have L greater than equal to 1, in that case the transcendental equation is V root over of 1 minus B j L minus 1 v root over of 1 minus b whole divided by jl v root over of 1 minus b, which is equal to minus of v root over of b k l minus 1 v root over of b whole divided by kl v root over of b. So this is for the case when you have L greater than equal to 1, right? And for the cutoff condition we have b equal to 0, right? So for the cutoff b is 0, that means beta is k0 and effective, which is equal to k0 and 2. And you already know u is v root over of 1 minus b. And when b is 0, that means the cutoff u will be v cutoff, and w is v root over of b. That means the cutoff b is 0, so w should be 0. So by using this formulation and by using this formula in this transcendental equation, you can easily get what are the values for VC for different type of modes. So different modes will have different value of V for the cutoff condition. So if we list out some of the value, so this is for your case, like for different modes, what are the different cutoff value? So the first mode, it is LP01 mode. This is no cutoff, you can take it 0. And the second guiding mode, which is LP11 mode, it has a cutoff around 2.4048. And for the second mode, LP02 and LP21, these two has cutoff around same value, which is 3.8317. And the next higher order mode is LP31. This is cutoff around 5.1356. And next is LP12, which is a cutoff around 5.520, and so on. So you can see when V is less than 2.4048, we'll have only single mode, which is LP01 mode. And when V lies between these two parameter, these two values from 2.4048 to 3.8317, then we'll have two modes, LP01 and LP11. And when we will lie between these two values, 3.8317 to 5.1356. So, but the mode that will be guided is these four modes, right? So what I'm saying is, whenever the value of V lies here, but it is less than 5.1356. So we'll have all these four modes which will be guided inside the fiber. So to find out the value for wavelength, we have to use the condition that V value should lie between 3.83 172 5.1356. And all the parameters for the fiber it is already given. Let me see. So N1 is given 1.5, N2 is given 1.49, A is also given. So that means we can expand the value expression of V. So we have 2 pi, A is 2 pi A root over of N1 square minus N2 square over lambda 0, which should be less than 5.1356. So just put the value of A and 1 and 2. So this will be 3.8317. 2 pi A is 3 micrometer. And this is 1.5 square minus 1.49 square. Lambda 0, 5.1356. So this will give lambda 0 will be, so this is 3.8317. The total value will come around, if you check, this will come around 3.25774 over lambda 0 less than 5.1356. So lambda 0 will be 3.25774, 3.8317. It should be greater than lambda 0, and lambda 0 is greater than 3.25774 over 5.1356. So this value is, it will come around 0.8502 micrometer, greater than lambda 0, greater than 0.633 micrometer. So to guide all this mode, we should have a source which has wavelength in between this maxima and minima range. Okay. So here in the graph also you can see the fiber, the step index fiber cannot allow, it can't allow guiding of three modes, because all the two modes is allowed, LP01, and LP01 is always guided inside the fiber. LP11 will be guided when it is less than, when it is greater than 2.4048. But for the third cutoff, we can see there are two guiding modes. One is LP02 and LP21, which has cutoff around 3.8317. So that means if V value is greater than 3.8317, it's not like three mode will be guided, it's like four mode will be guided. So that means the step index fiber cannot allow guiding of three modes. It always allow guiding of four modes whenever the V value is greater than 3.8317. So this is the conceptual one. And okay. So let me move to our next problem. So it is also a step index fiber, which is, sorry. Consider a step index fiber for which the single mode operation lies in the range lambda greater than 1.223 micrometer. Calculate the refractive index of the cladding layer if it is given that A is 4.2 micrometer and delta, which is the refractive index difference, it is 0.003. So this is also a simple question. It's like if you know the condition, you can easily find out what is the refractive index. So for single mode operation, what we want that the V value it should be less than 2.4048. So this you can write it as 2 pi over lambda A numerical aperture. It should be less than 2.4048. So that means lambda should be greater than 2 pi A Na over 2.4048. So this value it is already given in the question. You can see it is given the single mode operation lies in the range lambda greater than 1.23 micrometer. So that means this value is equivalent to 1.23 micrometer. So we need to find out what is the value of N2. So if we recall, we know delta is N1 square minus N2 square over 2N1 square. So N1 square minus N2 square root over F, which is numerical aperture of the fiber, it is equal to N1 square root 2 delta. So let us calculate first. So 2 pi A is given 4.2 micrometer and numerical aperture is N1 square root 2 delta. Delta is given 0.003. That means 2 delta will be 0.006 over 2.4048, which is equal to 1.23 micrometer. If you solve it, you can get the value of N1 first. So N1 will be 1.23, 2.4048 over 2 into 3.14, 4.2 square root 0.006. So this value will come around 1.45, right? And for the N2, you can just use this formula to find out what is the value of N2. So N2 you will get it will be square root N1 square minus 2N1 square delta. So that means this is N1 root of 1 minus 2 delta. N1 we have already calculated it. It is 1.45 and 2 delta it is 1 minus 2 delta will be 0.004. So this will come minus 0.006. So this will give 1.446. So that means for this single mode operation, we have the value of N1, it is 1.45 and the value of N2, it should be 1.446. Okay. So this is a simple question. So we'll solve simplest one, then we'll move to a more difficult one towards the end of this session. So next question, it's saying determine the cutoff wavelength for the single mode and the dual mode operation for a step index fiber with refractive index N1 is 1.474 and 2 is 1.470, which is a core radius of a 4.5 micrometer. So we have N1 1.474 and 2 is 1.47 and the core radius is 4.5 micrometer. So whenever you are trying to solve this kind of question like the cutoff condition and the cutoff wavelength, the cutoff value, so don't mix up the planar waveguide with the step index fiber. Okay, so most of the time what will happen? So Lina, if you have any query, then let me know. I can unmute you. But for the time being, I have muted your speaker. Okay. So, okay. So what I was telling is, so whenever you are trying to solve this kind of uh, questions, so you know that for the step index fiber, we have the cutoff value 2.4048. This is for the single mode operation. But for the planar waveguide, step index planar waveguide, we have the cutoff value, which is pi by 2, right? So don't mix up these two values. So be careful while solving the problems. Okay. So for this one, for the fiber, for the single mode operation, we have V should be less than 2.4048. So single mode means it will allow only the LP01 mode to be guided inside the fiber. So just use the expression for V, which is 2 pi over lambda 0 A square root n1 square minus n2 square, which should be less than 2.4048. So all of the values are already given. We know the value of A, N1 and N2. So lambda 0 must be greater than 2.4048 over 2 pi. A is 4.5 and N1 is 1.474 and N2 is 1.47 square. So this will give a value around 1.28 micrometer for the single mode operation. And the guided mode will be LP01. So for the dual mode, what are the modes that will be guided for a step index fiber? So it would be LP01 and LP11. This mode will be guided for the dual mode operation. And for that, if you see the curve, the VV curve, you can see the V values. It should lie in this range. That is 2.4048 to 3.8317. So for dual mode, so for the dual mode operation, we have the V value 2.4048 to 3.8317. So just use the formula for V, which is 2 pi lambda 0 A square root n1 square minus n2 square. It should be less than 3.8317. So that means we have 2 pi a square root n1 square minus n2 square over 2.4048 should be greater than lambda 0, which is greater than 2 pi a square root n1 square minus n2 square over 3.8317. So A is already given, it is 4.5, N1 it is given 1.474 and N2 it is given 1.47. Just use this. If you calculate it, it will come around 1.28 micrometer greater than lambda 0, and this value it will come around 0.8 micrometer. So whenever the wavelength it falls in this range, then it will allow both the LP01 and LP2, LP112 to be guided inside the file. So just remember the cutoff condition. From that, you can easily find out what is the range of wavelength or what is the range of V value, what is the range of core radius or any other fiber parameter for the single mode, dual mode or multi-mode operation. So let us move to our next problem. Please go through the question once. So we have two different step index fiber which has the same value of V at some wavelength. So how will their Gaussian spot sizes be related? So if you recall, the Gaussian spot size is nothing but W. And there is one formula for this. Whenever the value of V it lies between 0.8 to 2.5, then we can write W by A as 0.65 plus 1.619 V to the 3 by 2 plus 2.879 over V to the 6. This we already know, and it's given they have the same value of V. So that means this right hand side it is equal for the both the fiber. So if we say, let us say the spot size in first fiber is W1 and the core radius is A1. So this will be equal to W2 over 8 because the LHS RHS is equal. So that means W1 by W2 it should be equal to A1 by 8. So this is the relation whenever you have same value of V for a different step index fiber. Okay. It's not like they are independent. So whenever let us say W1 is greater than W2, then the core radius of first fiber should be greater than the core radius of second fiber. So let us move to our next problem. So we have a refractive index profile. So there is a single mode fiber with the following refractive index profile. NR, it is equal to N1 when R less than equal to A, N2 between A, R, B, and it is N3 between B, R, C, and it is N4 for R greater than equal to C. And it is also given that this value, that is N2, it should be greater than N1, should be greater than N4, and it is greater than N3. So write the modal field expression in all the regions. So first, what you have to do, you need to plot what is the refractive index profile first. So we have three reasons. Um, sorry, four reasons. One is around A, one is between A and B and C, and one is greater than C. So let us say this is reason 1, reason 2, reason 3, and reason 4. In reason 1, we have N1. So the highest value of refractive index is in between A and B. So that means this is highest, which is N2. The next highest is N1, which is in the region R less than A. So let us say this is around this value N1. So this is a step index fiber. And the next highest value is N4 between the region R greater than equal to C. So that means this N4, it is less than N1, but it is greater than N3. Say it is N4 and the lowest value is N3, which is in the region B and C. So let us say this is C. So we now know the refractive index profile. Now identify the core region, which is that is the region where the total internal reflection will occur. So from the profile you can see the highest value is N2 and the next highest value is N1. So that means if the value of beta, so this we have already discussed what is the condition for beta for the guided ray. So in this type of profile, when we have more than one core layer, the beta value should be less than the highest value, K0 and 2, and it should be greater than the next highest value, which is less than less than N2, which is N1, right? So this should be K0 N1. So if beta lies here in this region, we'll have guided mode only in the core region, and in the cladding it will be exponentially decaying. I think this concept is already clear. We have solved more than 2-3 problems regarding this, right? So for the modal field in a step index fiber, what we have psi A, R phi S, R of R, phi of phi. Other than the exponential term, we have the radial part and the phi part. So this you can write it as a AL over JLU, JL UR by A, sin phi, sin L phi, and cos L phi. So this is for R less than A, that is inside the core. And outside the core, if you recall, we have AL, KLU, KLW, KLW R by A, sin L phi or cos L phi for R greater than equal to. And U is, this is A square root A0 square and 1 square minus beta square, and W is A square root beta square minus k0 square n2 square. N1 here is, so this you can write it as, instead of N1, the highest refractive index here we have N2. So this would be N2. And the next lowest is N1. So here the index is interchange because depending on the refractive index profile here, N1 is N2 and N2 is N1. Okay, so now let us see the modal field profile. So for R less than equal to A, what we have? Beta is greater than K0 N1, right? Because here the value of beta is here, this purple line, which is greater than K0 N1. So that means we can write it is similar to a solution for the cladding layer. So psi in region 1 R5, it would be AI KL W in the region 1 KL WI R by A sin L5 and cos L5. What is the value of WI here? It is square root A square beta square minus K0 square N1 square. So be careful whenever you are writing equation for this kind of optical fiber. So don't confuse between N1 and N2. Depending on the value of the refractive index profile, we can have different value of WI in different ratio. So next in reason ARB, so what we have? So in this reason beta value it is less than K0 N2 and it is greater than K0 N1. So K0 N1 beta K0 N2. So that means the solution would be, it is similar to a core or the Bessel solution in the core layer. So this would be A2 U L 3. This is J, right? J JL U2 JL U2 R by A sin L5 cos L5. Similar to a core layer. Now for B R C. So between this region, in this region also it is greater than K0 N3, right? So this value is N3 here. So that means the solution would be similar to a cladding solution. Beta is greater than K0 N3. So that means we have psi 3 R5 as A3 KL W3 KL W3 R by A sin L5 and cos L5. So W3 now would be square root A square beta square minus K0 square N3 square. Similarly here it is U2, it would be square root a square k0 square n2 square minus beta square, right? Hmm. In the last reason, that is for r greater than equal to c. So here also we have beta greater than k0 and 4. So that means we have beta which is greater than k0 and 4. So solution would be similar to the cladding Bessel solution in the cladding layer. A4 KL W4 KL W4 R by A sin L5 cos L5. And W4 is square root A square minus beta square minus K0 square and 4 square. So if this kind of profile is given in the question, you can easily find out what are the solution in different region. And by using the boundary condition, you can calculate what are the constant value, what is A1, A2, A3, and A4. Just equate the field and the derivative of field at the boundary. Okay. So I think this problem is clear to you. If not, feel free to ask me anytime. Okay. So let us move to our next problem. Please go through the question once. So the next problem is to find out what are the number of zero values in the r and phi direction, except at r equal to 0 for the LP35 mode. So if you recall the transverse field profile, we have, if you go in the phi direction, we can find 1 0 or 4 0 for the mode profile. Also in the r direction, we can have the mode profile which is tending to 0 other than the origin point, which is r equal to 0. So how can you approach this type of problem? So when we have the given profile that is LP35, then how can you find out what are the total number of zero in the uh, phi direction, which is this direction, and in the r direction, which is radial direction. So this is phi direction, this is the radial direction. So when you are given this type of problem, so you just need to recall that so number of zeros, to find out the number of zeros in the phi direction, that is the azimuthal direction, it is equal to 2L. L is already given, so you can find out what is the number of zero in the phi direction. And for the r direction, the number of zeros in the r direction, it would be equal to m minus 1 other than the r equal to 0 point. So this already doesn't include the r equal to 0 point. So for LP35, we have L equal to 3 and M equal to 5. So that means the number of zeros in the phi direction, it would be 2 times of L which is 2 times of 3, which is 6. And in the r direction, we'll have m minus 1, which is 5 minus 1, which is 4. So we'll have 4 zeros in the r direction for this mode profile, and we'll have 6 in the phi direction for this mode profile. So answer would be uh, D, 4 and 6. Okay. Let us move to our next problem. Next problem is to calculate what are the total number of modes without including degeneracies. So we have a step index fiber with refractive index N1 is 1.5, refractive index N2 is 1.48, and A is 4 micrometer. Calculate the number of modes without including degeneracy at wavelength 1.3 micrometer. So let us see. We have N1 is 1.5, N2 is 1.48, A is 4 micrometer. So to calculate the number of modes, we need to find out what is the value of V parameter, which is 2 pi over lambda 0, A square root, N1 square minus N2 square. So just use the values. 2 pi A is given 4, N1 is 1.5 square, and N2 is 1.48 square. Over lambda 0 is 1.3 micrometer. So this, if you calculate it, it will come around 4.71736. So, which means the value for V, it is between 3.83172 to 5.1356. And if you see the graph, where is the graph? So we have one plot. Yes, this one. Okay, so it's better to see this one. So V value, it is between this one. So that means it will allow LP01, LP11, LP02, and LP21. So the total number of modes that will be guided will be 4 for this waveguide. So if you do not include the degeneracy, then the total number of modes will be 4. Degeneracy, by the term we mean, so we can see the modes can have sin L phi dependence or cos L phi dependence, right? So depending on that, each mode has twofold degeneracy in the phi direction. And for also for each mode we have X polarized and Y polarized. So we are not including these terms like the polarized term as well as the phi dependence. So if you do not include this, we have total number of modes as 4. Okay. So answer would be option A. LP01, LP11, LP12, LP2. LP02, not 02. Yes. So let us move to our next problem. So let me read out the question for you. So it is given if the spot size of a single mode fiber it is 3 micrometer and 4 micrometer at two different wavelength lambda 1 and lambda 2 respectively. So then which one of the following relation holds? So we have a same fiber which has different spot size at different wavelength. So W1 is, so can you calculate it? Can you tell me which relation will hold for this case? If we are given W1 is 3 micrometer for lambda 1 and W2 is 4 micrometer for lambda 2. Any answer? In option 1, we have lambda 1 equal to lambda 2 because they are equal. Or one thing we can have is lambda 2 is greater than lambda 1. Other thing we can have is lambda 1 greater than lambda 2. Or last option is that we cannot relate lambda 1 and lambda 2 based on this information. So which option? Option A or B or C or D? Anyone? So how can you relate spot size with wavelength? So one relation we already know that W by A it is 0. Spot size depend on the radius, right? Yes, spot size depends on the radius, co-radius A. It also depends on the V parameter of the fiber. If V parameter is high, then the spot size would be low. Okay. So whenever you have higher value of V parameter, the mode will be the allowed modes will be confined inside the fiber, more confined, highly confined inside the fiber. So that means the spot size will now decrease. Okay. Whenever V increases, the spot size decreases. This you can mathematically can see also. Conceptually, we have the higher the V, the lower the spot size. Mathematically, we can relate W by A. It is 0.65 plus 1.619 over V3 by 2 plus 2.879 V6. So you can see here W by A, it is, if you neglect this term, you can see it is inversely proportional to V, right? So if you let us take, so this is inversely proportional to V. Qualitatively, it is inverse. We are not considering if you consider the power also, it is okay. So W by A is inversely proportional to V. Now, for lambda, you can express V in terms of lambda. It is lambda over 2 pi numerical aperture over 3 by 2. So that means W1 by W2, it should be lambda 1, lambda 2 over 3 by 2. So lambda 1 by lambda 2, we have W1 over W2 over 2 by 3. And W1 it is already given. It is 3 by 4, 2 by 3. Here you can see the value of lambda 2. It is greater than the value of lambda 1. So if you calculate it, it will come around lambda 2. It is greater than lambda 1. So it also depends on the wavelength of the operating wavelength of the guiding mode. So it's not like they are not related. So we have option C. Lambda 2, it is greater than lambda 1. So whenever you are trying to solve this kind of problem, always try to recall what is the concept related to this. Not only the formula, but what is the concept? What will happen when we increase V? What will happen when we decrease V? So depending on that, you can easily uh, know what is the solution for this. Okay. Okay. So let us move to our next problem. So there is a transverse field profile that is given to you, and it is telling to identify the LPLM modes shown in the figure and write the mathematical expression for its model field pattern. So can you tell me the LPLM mode? Which LPLM mode this correspond to? So we have solved this kind of problem in the previous question. Just recall once. L is 2. Okay. And what is the value of M? So L equal to 2, you can get it from by, so if you recall, in one of the question, I told to find out the number of zeros in the phi direction, that is in the angular direction. In this direction, the number of zeros, it will be 2 times of L. I think you have used this formula to find out what is the value of L, because here in the profile you can see when you go from this, when you take a 360 turn, you can see there is a 0 here, there is a 0 here, there is a 0 here, and there is a 0 here. So that means 2L is 4. So we have L equal to 2. This is correct, L equal to 2. Now for the M. So M, you can calculate it by saying the number of zeros in the radial direction. So the number of zeros in the radial direction, it is given by M minus 1. So just use this M minus 1 and let me know the answer. So just look at the radial direction. No, it's not 1 actually. So it's 2. So M minus 1, this formula is for the case where we have This tells number of zeros in the radial direction except at r equal to 0. So we are not going to consider r equal to 0 point. So let us see. This is for 5. So when you move, let me take this card. So when you are going, okay, going in this radial direction. So this is the radial direction, right? So you can see there is a 0 here that we are not considering the origin point, but there is a field here. Now in this region, the field is 0 and there is a field. So don't consider these reasons and the reason where we have origin. So the far field region, don't consider it. The origin and the far field, don't consider it. Only the reason between the mode profiles. Here you can see there is a 0 here in the radial direction. Similarly, for this also there is a 0 here. In the radial there is a 0 here and there is a 0 here. No, M is not 3, M is 2. Because don't consider these zeros. This 0 don't consider, in this region don't consider it. Only the number of 0 in between the modes. So you can see there is a, so we are ignoring the origin point. This is clear. Now we have a mode and the mode, it is now it is 0 in this region, this region. Now there is a non-zero field here and this far field region don't consider it. Okay. So you can see there is a 1 0 between this mode profile, like in every direction. So that means m minus 1, it would be 1 only. So m is 2. Similarly, let us take a case like if we have this kind of situations. So there is a field here also. Then what will be the value of m? So this is for the assumption, like to just know whether the concept is clear or not. Let us say we have this kind of profile. So just let me know the value of n. Yes, m will be 3 in the case. Right. Okay. So for this modes, for the given fiber, given profile, we have LP, L is 2 and M is 2. LP 2, 2. So Lena, do you have any? Okay, here the radial profile is same in all direction. What we have different profiles in that case will add. So mode profile, it's if I recall. So I think you mean uh, different profile. You mean I think let us say this is like this, and in one case it is there, and in other case it is not there. I think you mean this kind of situations, right? So I don't think this will be the case because the modes that is allowed, these are solution of Maxwell's equation, right? So they interfere with each other to give this kind of profile. So these modes will always be symmetric mode because kind of uh, what I can say then other than this. Um, The perfect answer for this case is it's like these are Maxwell's equations, solution for the Maxwell's equation inside the optical fiber. So in most of the cases, we will find symmetric modes only. So let me see whether there is a case where we have antisymmetric mode profile. So if there is, I will let you know in the next session. Okay. This M-1 rules comes from how the Bessel function crosses x-axis, right? Yes, you are correct. So these are based on the Bessel's functions. So uh, we of how the Bessel's function the Bessel function behave in phi direction and in r direction. So by using the profiles, we have just condensed into a formula like M-1 for the radial direction and 2L for the phi direction. Okay, so there is one part that still remains in this question. What is the mathematical expression for its mode profile pattern? So now you already know what is the value of L and M. So based on this, uh, psi R phi. So this should come around A inside the core. It will be A J2 UR by A over J2U sine L phi, which is 2 phi. Why it is sine 2 phi? Why not cos 2 phi? Why we are taking only single polarization like cos by the angle in which I have my zeros? Okay, you are correct. Like you can see here at the 45 angle, or if you are meaning the zero, like at pi by 2, we have zero values, right? So if you put 2 pi and 2 into pi by 2, this will give a value of pi, and this sine pi will be 0. So that is why we are taking sine 2 pi. And other thing you can see here also at 45 angle it is non-zero, and it is only possible when 2 pi is pi by 2. For sine 2 pi by 2. So what I mean, if it is non-zero at pi equal to 5 by 4, that means 2 pi is pi by 2. So it is non-zero at pi by 2 angle, which is sine function. Okay. Okay, this thing is clear. So this is for inside the core. And outside the core, we have k function, k2 w r by a, k2 w sine 2 pi for r greater than a. This is for r less than a. Clear? Okay, let us move to our next problem. So let me read out. So there are two parts for this question. So part one, write down the mathematical expression for the model field patterns psi r phi and the eigenvalue equation for determining the propagation constant of the LP12 mode of a step index 5. So we have LP12 mode. So that means L is 1 year and M is 2 year. So modal field pattern, always remember what is the expression. So psi R phi, it should be A JL. JL is J1 U R by A J1 U. And this is double degeneracy, which is sin phi, sin L phi, and L is 1, so sin phi and cos phi inside the curve. And for the cladding, we have K1 W R by A K1 W sin phi cos phi. Or so this is for R less than equal to A. This is for R greater than A. And U is A square root K0 square N1 square minus beta square. And W is A square root beta square minus K0 square N2 square. And the eigenvalue is, it is nothing but the transcendental equation, right? So we have for LP12, we have L equal to 1. So just use the eigenvalue equation. So in the first question, we have seen two transcendental equation. One is for L equal to 0 and one is for L greater than equal to 1. So just use L greater than equal to 1, which is V root over of 1 minus B, JL minus 1, V root over of 1 minus V, JL, V root over of 1 minus B, minus V root over of B, KL minus 1, V root over of B over KL V root B. So L is 1 year. So that means we have U. So V root over of 1 minus V is U. And this is V root over of B is W. So we have U J0 U by is J1 U equal to minus of W K0 W over K1 W. So to find out what are the solution for LP1 mode by using any software, so you need to implement this formula. For LP12, you need to use this. For fundamental mode, it would be different. So just find out what is the transcendental equation corresponding to that mode and define the parameter for that. Then you can easily find out what is the total number of mode, what is the propagation constant for that mode. Okay. We'll see in this session. Okay. Now for the second part. In a step index fiber with N1 1.5, N2 1.49 and A is 3 micrometer. Calculate the range of lambda 0 for which only LP01 and LP11 mode will exist. Okay. So I think you can easily solve it, right? So can you let me know the answer? we have, so let me give you the parameter. N1 is 1.5, N2 is 1.49, and A is 3 micrometer. So now you need to find out what is the uh, range of lambda 0, for which LP01 and LP11 mode will exist. So let me give you the condition also. For this, we have already seen, for these two modes to exist, we need to have V parameter, which should lie between 2.4048 to V and 3.8317. V, you already know, this is 2 pi A lambda root over of n1 square minus n2 square. Okay, so let me calculate it. Lambda 3.8317. So that means we have 2 into 3.14, 3 square root 1.5 square minus 1.49 square over 2.4048 greater than lambda 3.143 square root 1.5 square minus 1.49 square. So this will come around 0.8. So this will be 1.355 greater than lambda, which should be greater than 0.851. So just practice this type of problems, okay? So that your concept is clear. Okay, so let us move to our next problem. So do you have any query up to now in any of the problem? Okay, so let me know the answer for this. Calculate it. So it is given, consider, so consider a step index fiber with N1, it is 1.5, N2 is 1.48, and A is given 4 micrometer. Lambda 0, it is given 1.3 micrometer. Calculate the total number of modes, including degeneracy supported. So, if we are given this parameter, then what are the total number of modes, including degeneracy? So, first, you need to calculate what is the V parameter. So, what is the value you are getting for the V parameter? 1.179. V parameter. Uh, I don't think so. It is correct. So V it is 2 pi A over lambda 1.3 square root 1.5 square minus 1.48 square. So this is you are getting 1.179. Yes, it should be 4.7. So this value is around 4.7. So now you need to look at the cutoff condition, right? So this is greater than 3.8317, which is the cutoff for LP02 and LP21 mode, but it is less than 5.1356. So this is, if I recall, this is LP01, LP11, and LP02, LP21. So V value is lying here. So that means total number of modes that will be supported is, what is the total number of modes? How many modes will be supported if we are given V is 4.7? 4 without degeneracy, correct? So we have 4 modes, which is LP01, LP11, LP02, LP2. So if we recall, the whenever there is L equal to 0 there, this doesn't have phi degeneracy, right? Because this is azimuthally symmetric. When L is 0, it is symmetric in the phi direction. So that means for this case, we don't have any. So degeneracy, we have two types of degeneracy. Okay. One is in phi direction, one is for polarization. In phi direction, we have cos L phi or sin L phi. So each mode which doesn't have L not equal to 0, these are two-fold degenerate. And besides that, we have polarization degeneracy, one for X polarization and one for Y polarization. So when L equal to 0, this term is not, it is not contributing to the degeneracy. So that means this will have two-fold degeneracy for X and Y. This will have two-fold degeneracy for X and Y. And this will have four-fold degeneracy because both cos alpha is sin alpha and X and Y polarization. And this will also have four-fold degeneracy because L is not equal to 0. So that way, that means we have total number of modes, including degeneracy, will be 4 in 4, 4, 8, 12. Right? So total number of modes, including degeneracy. So when you include degeneracy, we have 12 modes. So answer will be option D. So is this clear? D. Okay. So now let us see the next problem. So it's always better to know what are the degeneracy of a given mode, because so if you recall, whenever we have a bending in the fiber or whenever there is a stress in the fiber, so what will happen? So this degeneracy will be lifted. So like different the same mode with different degeneracy, this will have different propagation constant. So for now, this whenever the for ideal fiber, this modes will have same propagation constant. But whenever you introduce a bend in the fiber, so this degeneracy will get lifted off. Okay, so in that case, you can't treat each mode as a same mode. You have to treat it differently. For the next problem, we have calculate the Gaussian spot size in micrometer uh, of fundamental mode at 0.9 micrometer wavelength for an step index optical fiber with numerical aperture equal to zero point 0.1 and A is 3 micrometer. So you need to find out what is the Gaussian spot size. Okay, so V is, so we have wavelength lambda, which is 0.9 micrometer. Numerical aperture, it is given 0.1 and A is 3 micrometer. So first let us calculate what is the value of V. V is 2 pi over lambda 0 A to numerical aperture. So 2 pi lambda is 0.9, A is 3, numerical aperture is 0.1. So this is 2 pi by 3. So that means the value of V, it is now falling in the range, right? So if you recall, we have a formula for this, which relates W with the V parameter. Yes, this formula. So this is only valid when V lies between 0.85 to 2 point something, I think. 2.5. So that means we can use this formula for the time. Okay, now V is falling between 0.8 to 2.5. This will come around, I think, 2 point something, which is less than it will come below 2.5. So we have W by A is, yes, 2.09. Correct. So W by A, it should be 0.65 plus 1.619 over V 3 by 2 plus 2.879 V 2 was 6. So just put the value of V, which is 2.09. V2 was 6 means it will come 2.09 was 6. So if you calculate it, so W is A times 0.65. This this will come around 0.535, and this one it will come around 0.0342. So that means we have, and A is already given, I think A is 3 micrometer. Yes. So when you multiply it with 3, it will give you a value 3.7 micrometer. Okay. Answer will be option A. Okay, let me check whether your concept is clear or not. Once again. So this is for the your conceptual understanding. One is to identify. One is to 1 minute. Identify the following transverse modal field profile for from a fiber. So can you let me know what is the LPLM mode for the first profile? L equal to 1 and M equal to 1. Yes, it is correct. So for this, we have in the phi direction, we have two modes, sorry, two zeros. One is here, one is here. So 2L is 2, that means L is 1. And in the phi direction, we are not considering the 0 point, and this reason where it is the far field region, right? Not far field, it's like the region where the field is not there. So across this radial direction, we have no zero values of R. So that means M minus 1 is 0. So M is 1. So this is LP11 mode. What about the second mode? B. L is 2 and M is 2. Uh, L is correct, both of you, because 2L is 4, right? Here in this direction, phi is 0, in this here and here. But for the M, so here you can see there is no 0 in this direction, right? 0 is not there. Field is always there, which is a confined field. So that means m minus 1 is 0. So m is 1 and L is 2. So we have LP to 1 mode. What about option C? I think this is clear, right? Radial direction may be a confusing one, but if you know how to locate it, how to see where exactly to locate it, then you can easily find out what is the value of m. Huh. Okay. What about option C? Lina 1, 2. Okay. I mean L is 1 and M is 2. M is 2 and L. Yes, both are correct. Here there is 1, 0 in the radial direction in between the mode. And here, phi direction here, there is a 0 and there is a 0. So we have LP 1, 2 mode. And the last option, D. Yes, L is 2 and M is 2. Yes, both are correct. Phi direction, we have 0 here, 0 here, 0 here, 0 here. R direction, we have 0 in between this. Correct. I think the concept is totally clear to you. Okay. So this is what we have seen now. That is, this is LP 2 mode. So you have already solved what is the first part of this question. So identify the LP LM mode shown in the figure. So this will have LP 2 mode. Now write the mathematical expression for its modal field pattern. So just let me know whether it will have cos phi dependence or sin phi dependence. So this is, yes, it will have cos phi dependence. So for the core, we have A J2 U R by A by J2U cos L phi, because the field is 0 at 45-degree angle, right? So phi 45, that means 2 pi is 90. So at 90 degree, the field vanishes, which is for the case cos function. So this is for r less than equal to A, and for the cladding reason we have K2 WR by A, K2U cos 2 phi for R greater than equal to A. Okay. So this is what I wanted to solve or I wanted to do in this live section. So now let me give a hint about how you can solve the transcendental equation using MATLAB. So for a given question, you will be given what is the refractive index profile, what is the value of n1, what is the value of n2, what is co-radius, and the question may ask about ha, uh, what is the total number of modes that is supported by the fiber without degeneracy or with degeneracy, or what is the propagation constant for this given mode. So for this, what you need to do? So you know that all depends on the V parameter, right? So the first thing that you need to calculate is what is the V parameter for that given pipe. So let us say we are given. Uh, so let me write. So I think all of you know what is the language of MATLAB. You can define a parameter. So it's a three steps. One is to define the parameter. So you have to define the parameter. Then you need to implement the transcendental equation to find out the intersection point. So the point where J and K they intersect. Then we have to just print the results. So the two first step is to define the parameter. It's easy. So just give a variable a name to a given parameter. Let us say we have the core radius, which is 5 micrometer. So let this you can write it as A is 5 e to the minus 6, which is core radius. Okay, and for the lambda is also given, so you can define a variable lambda 0, which is let's say it is given 1400 nanometer. So this you can write it as 1400 e to the minus 6. And you can write the comment. So this is core radius. This is free space of, let's say it is operating wavelength. And next is we have the refractive index of core, which is 1.5. This is core refractive index. And N2 we have 1.48, which is cladding refractive index. Next thing we have is the K0 value, which is 2 pi. This is the language that we use in MATLAB. 2 pi a over lambda 0. This is free space wave number. So this is all about defining the parameter. Now what you need to do, you need to calculate what is the value of V. So V, if you recall, we have V is 2 pi a lambda 0 multiplied by square root, which is a squarity function, n1 square minus n2 square. So this is V number, right? So now let us say we want to find out what is the solution for the transcendental equation for fundamental. So fundamental mode is LP01 mode. This is LP01, right? LP01 mode, if you recall, let me go back to first. So, okay. So you have to use this formula for L equal to 0. So from this, you can see if you use V root over 1 minus B is U and V root over of B is W. So this will give okay, here. So the transcendental equation for the fundamental mode, it is U J1U by J0U on it. Mhm. Yes. So this is equal to W K1 W by K0 W. So what you can do is to define a value of V, sorry, value of U. So you know already the value of V. Now you can, what you can do, you just create a array of U where which will fall around the allowed solution, which will and using the array of U, just calculate the what is the LHS side of this and what is the RHS side of this. So what I mean is, so how can you calculate what is the allowed value of V U? So for the allowed value, you know that U is nothing but V root over of 1 minus B, right? And B value, it is lying between 0 to 1 for the guiding mode. So that means what will be the range of U then? When B is 0, U is V, and when B is 1, U is 0. So that means for the guiding mode, the range of U should be between 0 to V. So what you can do, you know the value of V. You already calculated it using this formula. Now, let us say we have V is 11 now. So what you should do, you just discretize this point. Like take some points between, take a number of values like 500 points or 10 points in between this range between U and V. So for that, what you can do, you can use the line step function. So U values, you can use line step, line space between what is the minima, what is the maxima, and how many points you want. Like let's say 1,000 points. So this will divide this range by 1,000 equal parts, and this will store this value of U. Okay. Now to just simplify the process, what you can do. So this is to find out what is the U values to solve the transcendental equation. So now what you can do, just define a variable for this part and define a variable for this. So name it, name the LHS side and RHS side so that you can use it in the loop. So let us say we have, so LHS side is, this is, okay, before that, what we can do, we can initialize the values for this LHS and RHS side, right? So in any kind of language, you already know, you need to, so it's always a good practice to give some values in the initial condition. So for this, let us say initially they are all zeros. Okay. So for this, you can see it is, let us say, let us give zeros values with size u values. So what it will do, it will create a array which is size of u values. So whatever the size of u values you are getting here, this will create a same array with zero values in all places. So now we are initializing the LSS as zero values. Similarly for the RHS, it is zeros, size u values. Okay, now to solve the transcendental equation, what you can do, you can use a loop. In different data points, like different u values, you can use a loop. Like let us say, you can use for loop, but that, right? For loop which runs from value I equal to 1 to u value, which is the maximum value. So use the for loop, and inside the for loop, what you need to calculate? You need to calculate the value of w, right? W is square root v square minus u square, right? If you recall. So just use the language of MATLAB, like square root, you can write it as sqrt, right? V square, you can write it as v to power 2, you can write it as u to power 2. U values, you already know because we have used line shape function to discretize the points. Now you know the u value and w value, so just compute the LHS. So LHS would be, it is u times. So if you see, this is u times Bessel function J1 and Bessel function J0. So for this, you can write it as Bessel J1u um, over Bessel J0u. This is equivalent to of saying u J1 u over J0u. Similarly for the RHS. Okay. So just use Bessel K. So for that we have K. So we have W multiplied by Bessel K 1W and Bessel K 0W. Yes, it's an inbuilt function in MATLAB. You can just write the uh, this write the name, and you can easily uh, find out what is the LHS and RHS value. Okay, so for each index of u, just find out what is the LHS side and what is the RHS side for each data points. After that, what you can do, you just use the, so you have all the values of all the values of LHS and RHS in different point. Now what you can do, you can use the find function to find at which u value this LHS and RHS they are intersecting with each other. So for that, what you can do, you can use the function find. Find is absolute LHS minus RHS which is equal to minimum ABS LHS minus RHS. So so just give it a name. So just give a name to this functions. Let us say this is intersection index. So what it will do, so it will find out what is the at each data points, like we have data points at I value, right? At each data points, it will find the difference between the absolute difference between LHS and RHS, and it will find out what is the minimum difference you are getting. Minimum is they are closer to each other. That is LHS is approximately equal to RHS. So this is what we want. So this will find out the index, the U index. So after getting the U index, you can find out what is the U solutions, which is nothing but U value at that index point. Let us say we are getting the point, we are getting the solution at index 4. So this will, so index 4 here. So this will calculate the U value for that. So that is the point where LHS is approximately equal to RHS. So this will give the U solution. So now you know the U solution. From that, you can find out what is the W solution, right? By using square root V square minus U square. And from that, you can find out what is the beta value also. Because beta is nothing but, if you recall, U square is A square, A0 square and 1 square minus beta square. This value are already known. So if you know U solution, you can find out what is the B solution for that. Okay. One thing just you need to see here is to set the limit between 0 to V. Otherwise, you will get imaginary value and you won't get any. You will get the plot, but you will see error in that. Okay. So just set the value between 0 to V. So this is one way of approaching the transcendental equation. There are many ways. So you can use your own method to find out the solution. Okay. So just define the parameter, and next thing is to find out the V value. Then next thing is to discretize the point U value between 0 to V. Then just initialize the LHS and RHS value to 0 and use a loop to find out the LHS and RHS at each data points. From that, just find the index where you are getting the closest value using the find function or any other function that you can think of. From that, just use U solution at that index and find out the beta values for that. Okay. So this is the general flow chart for approaching the transcendental equation. Can you please say the slides a bit? Okay, I will share it by tomorrow. I will upload all the slides. Okay, don't worry about that. So this summarizes our live section, the things that I wanted to solve. So I think whatever I have solved, it is clear to you, and it is also maybe it will be helpful for you to approach the assignment properly. Okay. Please share the previous one also. Yes, I think I haven't shared the slides. I have just uploaded the slide one, not the slides for all the tutorials from starting from two. Okay. So I will set the slides by tomorrow morning. Don't worry about that. Okay. So thank you for joining the live section. We'll meet on next Monday, same time from 6 to 8. Okay. So thank you. Bye everyone.